computer. Perfect, thank you.
Perfect.
Now we are there. Okay, so welcome to you. This is lecture number 7 of the FIS 140 class this semester, and let's go to full screen, which is view. And this is what was somehow, there are two aspects. We've been looking at diffraction in general. Starting from interference, we went into diffraction. We found a diffraction of a slit. This is optical diffraction. When you reduce the sizes of the obstacles that are facing the electromagnetic waves, you get into a diffraction that is slightly different. And this is the case of when you have a solid, the characteristic length of the solid of whatever makes diffraction in a solid is comparable to the separation between planes in the solid. That's essentially, or the distance between atoms. The distance between atoms, the wavelength is in the angstroms. Okay, this wavelength in the angstrom range are comparable to these distances in the angstrom range are comparable to the wavelength of lights of the same length, the angstrom. And this is exactly what X-rays does. So X-rays will actually diffract from an ordered crystal in a solid, okay? And I'm gonna try to show you what the main features are. Let's start with this diagram here. We generate electromagnetic radiation of X-rays by actually heating up a filament and accelerating electrons that collide with this is the cathode here, this is the anode. This is exactly the way it looks for the X-ray tube your dentist has at the office, okay? And there's a piece of metal here where the electrons collide. And when they do that, they lose all their energy. The energy you gave them as the acceleration of the energy, they lose the energy and they transform that energy in electromagnetic radiation that goes through a pinhole in this case and gets to your sample. And when it gets to your sample, it gets scattered in different directions. And this different direction that it gets scattered has to do something with the details inside the crystal. This is a characteristic I would say, oops, there you go. This is a characteristic view graph that you get with a photosensitive material that, you know, every point in there, this is like, you know, the X-ray photograph that you get out of the dentist, essentially, where the dark places here means that you have a high intensity and you get these beautiful patterns that somehow has to do with the symmetry the crystal has. This is a sort of a somewhat straightforward technique, but it has a few complications because there are a few things that you can learn from this technique only. And I'm going to try to explain to you how does it work. Essentially, let's first concentrate and let me can I do this spotlight? Yes. Okay, let me concentrate first in the scattering from the atoms of the top layer of a material. We are going to assume that the distance between every other instance in the material is a distance A, shown here, and the separation is a distance D between this layer and this layer, and we're going to assume that it's some sort of rectangular thing that goes all over the place, okay? So if I go in a plane inside, I'm going to separate it by a distance A in that, and you will have the same atoms again. So if we are looking, this is a plane wave of X-rays coming into this system, and my my model shows that when this plane waves is incident with a particular angle theta and comes out with an angle that is also theta in the incoming direction and the outgoing direction, all the amplitudes that are produced for all the atoms in the surface are in phase. Okay, so this is scattering only from atoms on the surface. You can see that this guy, this plane wave is in phase here, in phase here, in phase here, and from here on there's something different. This guy strikes this atom and is reflected in this direction, but this guy keeps going, keeps going, keeps going, and then is reflected. It happens that this difference in path from here to here is the same difference in path from here to there. Okay, so if the angle of incidence is measured with respect to the normal here, here the angle of incidence with respect to the plane. Okay, this is the plane, this is theta A. It means that if this angle here is theta A in the incident beam and theta A in the outgoing beam, these two things are going to be in phase. This is essentially what it shows. Here is in detail between the two atoms. Okay, so from now, the thing in the light pink ray here, from here to here, this is how much this guy travels up until it gets here, and this is how much they travel since they were completely in phase until they get there. The only way that these two things are going to be in phase is that this theta A is equal to that theta R. So the angles, the reflected angle and the incident angle are the same. So how do we call this? Why do we call it A? I don't remember what is the nomenclature here, but it doesn't really matter. This angle, the outgoing angle, and the incoming angle should be the same for this guy. Whatever radiation comes out of this guy and this guy should be in phase. If these two guys are in phase, well, these two guys are in phase, these two guys are in phase, the one underneath are in phase, on the other plane are in phase, everybody is in phase. So you get a huge reflection from all the atoms in the surface in a certain direction if you're looking at the same outgoing wave. Now, I want to see if I can get something special about the scattering from the first plane and the second plane. When I would see something that is that this guy and this guy are in phase. Okay, so this will be for a particular incidence angle. Okay, this angle in particular is showing here the difference in phase between this atom in the top layer and the atom right below it in the second layer. Okay, so this guy comes along and it goes out in if this is theta, whatever theta is here is the same theta here, because we want this guy to be in phase with all the neighbors in the same plane. But now I'm interested to know if the difference in phase of this guy that comes down here, this ray that comes down here, gets to here, travels to here, and travels to there. This thing in light rose color here is the additional path that the X-rays will have to travel to get to the source. But if this difference, which is the usual thing, is this is d, this is sine theta, is 2d sine theta, is equal to an integer number of wavelength, what happens is this guy and this guy will be in phase. So this guy, if this angle here is the same as this angle here, so we have this theta and this guy theta, it means that all the reflections of the X-rays from the surface of the crystal are going to be in phase. Also, all the ones on the bottoms are also going to be in phase. And everything that is visible in the crystal will be in phase. So everything will be reflected high. But in addition, if this particular angle now is such that the difference in path coincides with this relation, now these guys and these guys will also be in phase. So you will have an increased amplitude because of that reason. Okay, this is something. This is the way this technique works. And if you actually, what you do is you map when you produce a single wavelength here of the crystal, and you can get information about the symmetry, the distance on the planes, etc., on a solid. And this is one of the main tools. This is actually the original tool that was used to discover the distance between atomic planes and atoms in a surface. Okay, you know, very shortly after the discovery of X-rays, and probably Marie Curie has a lot to do with this. Okay, so that is sort of the time in the century that happened. So the beginning of the 20th century. Now I want to switch gears to a different problem. Also, that has to do with diffraction, and these are all applications. I want to mention the circular aperture resolving power. Okay, so when we have I don't have but you have in mind the diffraction from a single slit aperture. Okay, so you have a central maxima in the middle, you know, and then you have a lateral minima, and you have this sine x divided by x dependence as a function of the distance in the screen. Here, when you have a circular screen, it happens sort of roughly the same way. You have to remember that if this was a horizontal slit, you know, the difference for a horizontal slit will be when sine theta is equal to lambda over a. So that means a sine theta equals lambda. That means that actually the thing that is coming from the top of the slit and the one at the bottom of the slit has a difference in phase of 2 pi, which means that the thing actually goes all the way around, and the contributions from one extreme of the slit, the electromagnetic field from one extreme of the slit is actually in phase with the contribution from the other slit of the screen. And what that means is that the field has, you know, the small contribution of each one has gone all around in a circle to actually add up to 0. So that's why you get a minimum and in this condition. Okay, so one would imagine that in the case of a circular screen and a circular aperture like what I'm showing here, the situation should be fairly similar. Indeed it is. You get a central maxima, then you get a minima, then you get a second maxima, and these all decay as a function of the separation from the central minima, meaning this is not as intense as this is not as intense as that, and so on. Okay, and what is used to characterize this is this angle theta 1, which is the radius essentially of this bright central region, which is called the Airy disk, due to the guy that actually first described the theory to predict the position. Okay, so if we have depending on the size, if we have several objects, as I'm going to show in the next transparency, and we have apertures of different sizes, the effect of the diffraction with respect to this will be different. And this is what I'm showing here. Okay, so this is a series of sources being seen through a small aperture. You have that source, and here you can make up that you have two sources essentially, very close by one. So it's source 1, 2, and 3. So this is a small aperture, this is a medium aperture, this is a large aperture. So when one looks at this, it says, what the hell? Why would anybody use a small aperture for anything, you know? Well, you know, maybe he has a phone. He cannot be carrying along, you know, an astronomical telescope to look at things. And that's what happens. You know, diffraction, the size of the objects somehow induces a change in the diffraction pattern that you collect in a screen. And you cannot always optimize this feature because you cannot, you know, carry an optical, you know, an astronomical telescope with you, and you have to carry something smaller. So probably all of our pictures taken from a camera on the size of a cell phone has this effect on it. But the pixels are so very small that you can actually, you know, get away with it. Okay, so but this is not in the size of the pixels. That this is a limitation. The fact that the diagram look like this is not a problem of resolution of the pixels of the system, but it is essentially a physical limitation of the optical system where the light is going through. Okay. So here I have the first homework for you guys to work on. But let me explain first what it is. Okay. So the idea is the following. Did I write this up? No, I did not. Wow. If you remember the first minima in the case of a horizontal slit was lambda over A. Okay, where A was the size of the slit. Here, it's roughly the same thing with the difference that is there's a numerical number in the front, is 1.22 lambda over D. Now the diameter is the key thing. You know, with a big effort and probably 2 classes, we could actually calculate the Airy disk and whatnot. But at this point, I would like to actually not do that because it's not really the feature we have already learned. The difficulty is in the math of actually doing the calculation to calculate the intensity as a function of radius in this case. Okay, which is it's a bit more technical than what we did for the you know, the horizontal slit of width A, but you know it is essentially the same thing. Okay, so the numbers are not really that different. You know, the characteristic length has to be multiplied by 1.22. Okay, so if we have these two sources here, you know, this source that makes an angle that is theta between 2, and you know the angle theta of the image after the source will be the same because the light will travel all essentially in straight line through it, at least for the maxima. Okay, so you have that maxima, and you have the straight line, and then you can imagine that if I push these two objects far behind, this angle here will be much smaller. Theta min will be much smaller, and this angle here will be much smaller too. So this maxima and this maxima will start to be very close together. Okay, they will be so close together that you won't be able to actually differentiate them, one or the other. So there's one criteria which is called the Rayleigh criteria that says if you want to differentiate two objects going through a pupil like this, and what you have to do is the minimum angle that you know, if the minimum angle that you can have here in order for them to be different should be such that the maxima of one source correspond to the minima of the other. And you can see that that happens perfectly here. This is the oops, I'm sorry. This is the corresponding pattern for one slit. That's what I see here. And this is the other one is the corresponding pattern for the other slit. These two sources are not going to interfere. Why not? Because they are not coherent. They don't have, there's no information being transmitted here for the phase or whatnot. So essentially you get the superposition of both sources here without coherence effects or interference between the two sources, okay? So essentially you add up the amplitudes here, okay? Now, so there's a minimum angle and that minimum angle has to do with this criteria. So this is the homework here. It's not very well defined. It's an estimate. You have to estimate the distance at which you will see the lights of a car in front as two separate light objects instead of one. Because when will need one? If this angle is less than theta minimum. And if you move the car way distance in the road, you probably see the light coming from those two cars as a single source. And you will be able to differentiate it only when the car starts closing by. So my question is, give me a number, you know, it's 100 meters, 200 meters, 1 kilometer, you know, you have to, there are many things that has to be defined. What is the wavelength of light? What is the separation of the light sources? You know, I guess, what is the size of the pupil? You know, you have to estimate numbers here. The size of the pupil cannot be 1 centimeter because that's sort of the size of the eye. So the size of the pupil, what pupil? The pupil of your eye, because that's the object that actually allows the light to get through your pupil and get to the bottom of your retina, okay, and make an image there. But for that, we want the image in your retina should follow the Rayleigh criteria, okay? So the two maxima should be separated at least by that. So that's a good exercise. You have to, there's no good or wrong answer in this. You have to make a good estimate, okay? And it should be something that clearly you can test it with the experience here. What would that be, you know? So, all of you can drive, so you can actually figure that out, okay? Okay, let me go now into or go back into geometrical optics, which is a branch of optics where no diffraction, no interference happens, okay? And the only elements that goes here is our light sources. And if two rays of light, which originate from the same object, after going through whatever they go, they join back in space in one point, they will create an image of that point, okay? Of the point where the light originally came from. So those are the elements of geometrical optics. This is the simplest thing. This is the thing that allows the opticians to design your glasses. Every optical instrument, from a camera, telescope, essentially deals with geometrical optics. So that's why I'm going to spend the rest of the class actually trying to convince you that this is an interesting aspect. And it's very nice because this can be done. I learned it in my first year at the university. It has nothing to do, essentially, you get a few recipes and you can forget that the electromagnetic waves diffracts. You know that they do, you know, but here this is a geometrical optics is essentially ray optics with light of 0 wavelength. That's sort of, because something with 0 wavelength will never diffract. Yeah, we will never have lambda equals 0. So with lambda equals 0, this is straight here, so you will have only a line. That's what it is, okay? So you'll see only whatever it's you know, the bright spot, that is geometrical optics. Okay, so essentially some definitions: an object in optics is a region of space that produces lights or reflected. They are point objects, which is something that is you know, only from a point, or extended objects, and these last ones are formed by combinations of point objects, which makes sense. Yeah. The laws of reflection and refraction applies to transmission and reflection and interface. They apply to macroscopically only to smooth surfaces. So if the surface is smooth, whatever I do in this place will be the same of what I do in a different place. So that's what it is. So a point source or an object is something that emits a light in all directions. And when you see it, you know, this could be a real object or could be a you know, real object. It could be a real source, meaning emitting lights of its own, or it could be reflected light. It could reflect lights from wherever it's coming from. Okay. Okay. Now let's consider the reflection on a mirror. Look at this. So this is an object, and for each one of these rays, I do this. What did we learn from reflection and on a surface? We know that the angle of incidence should be equal to the angle of reflection. Now, in this case, the angles are measured with respect to the normal. So this angle should be equal to this angle over here. And this is done for every ray that arrives to this metallic surface, which is a bright, smooth surface that produces a reflection in this direction, in that direction, and you actually can see them in this with your eyes. But you're not seeing them directly. You're seeing them as they come from the reflection of a mirror. And look what happens. It looks like all the rays that you are actually seeing are being produced in a point behind the mirror. There's no electromagnetic field in this point, but simply because of the laws of reflection, your image that you're going to be seeing, it gives you the idea that this point that actually is in front of the mirror is actually behind the mirror. So this is an object point, the source of the rays, and this is the apparent position of the source. This is an image point, okay? And this image point is actually formed by the projection backwards of the reflected light. See, this is the reflected ray and this is a reflected ray. And if these two rays that were coming from these point sources intersect somewhere in the back of the mirror, it means that that point where they intersect, there is an image, the image of this point. Okay. This is Alice in Wonderland all over the place. Okay. Yeah. Okay, now let's consider the other aspect of this thing is that we have systems in which we have an index of refraction. So we have, again, straight interface. This is straight, smooth interface, and a ray being produced by a source underneath here. You can imagine this is a pool with water, and there is a flashlight underneath, and you are looking at the flashlight on top. Okay, and the light will come out. Since the index of refraction of water is around 1.33, then and the index of refraction of air is 1. This thing, when it arrives to the interface, the ray that is coming from the source will actually be deflected away from the normal. So if I draw the line here, which is the normal to the surface, the place with the higher index of refraction is close to the normal. The place with the lower index of refraction, the angle is longer, in such a way that Snell's law is still valid, okay? Meaning NA times sine NA theta A is equal to NB sine theta B, okay? That must happen in every point here, and it does. When we do that, we find that if we project the lines backwards from the refracted rays, we find that the point makes an image which is much closer to the surface than the actual point it is. This is the reason that when you are in a pool and you look yourself to your feet down, it looks like you're much shorter. You look funny, isn't it? I'm sure you have done that experiment before, so I don't have to advise. Well, then, you know, it's September and it's good. You can go to the pool. You can argue that this is a physics experiment, okay? And do this experiment. And actually, we get this sense of depth when we see an object simply because of the difference in angle that it makes, and our brain is already well trained for doing that. That the slightly difference in angles of the light coming from a source gives you the impression of distance, okay? And I'm not going to get into that because that's a whole complicated matter on itself, but that's the way we do it. The difference in angle gives you this perception of where the actual object is located, okay? So whenever you see a fish from the surface, it's not where you see, it's much deeper. That's something you have to understand. Let's see how the image forms in a flat mirror. This is a construction that we're doing, and whenever the thing is, whenever the virtual rays forms at the intersection of the extension, the virtual image, okay, like this is the virtual image, this is the virtual image, forms at the intersection of the extension of the real rays back from the reflecting or refracting surface. So this is the real ray. I extend it back, and where do they intersect? They form an image. If two rays if I do the geometry for two rays of the system and it happens to intersect in a point, it means that there are a lot more. That is essentially what it does. So whenever two rays intersect that originate from the same point, that's the key aspect here. So this ray originated from here, this ray originated from here. So I look back at the intersection, they intersect in this point, perfect. This is an image point. I'm unsure that if I found two rays intersecting in that point, there would be a lot more, okay? So this is the thing that we use to actually characterize the construction of an image in a flat mirror, okay? Let's see this image over here. So you're looking at this object through the mirror. So you're seeing the reflection of the image on the mirror, and so this light is going there and going there to your eye, okay? And this angle here must be equal to that angle there. This is the law of reflection. So the angle of incidence equal to the angle of reflection. So theta, perfect. So this guy goes there, goes to your eye, and somehow it gives the impression that comes from somewhere behind the mirror. This ray over here is reflected exactly back by the same way because this is the normal incidence. And the one that is reflected back, you can extend it back like this, and you can extend this guy back like that to find out where is the position of your image, okay? So it happens that by construction, this distance is common, okay? This angle we know is theta. These two angles are theta. By construction, this is alternate angles between parallel lines. So essentially they are equal again. So we know this angle is 90 degrees. We know by construction this guy is 90 degrees. Okay, we know this angle, then we know this angle is the same as this one. So this triangle here is exactly equal to this triangle here. So they are congruent triangles. And due to that, this distance, the distance at which the image is behind the mirror, is equal to the distance the object is in front of the mirror. This is the nomenclature we will be using. The object distance we will label as S, and the image distance in general we will label as at S prime. Okay, so all the rest of it I think I said already. So this is the vertex, because this is the vertex is the point where the light incidents normal to the surface. Okay, so no problem here. The apparent image is exactly at the same distance the object is from the mirror. Okay, perfect. We're gonna introduce at this point some sign rules that makes definitely no sense for flat mirrors, but they do make a lot of sense for concave refracting surfaces. Okay, so the object distance, let's read the definitions, is positive, is located on the same side of the reflecting surface as the incoming rays. Okay, in this case, this is the size, this is the reflecting surface. So the object is in the same side of the reflecting surface as the incoming ray. For this reason, S must be considered positive. Image distance. Image distance is positive, is located on the same side of the refracted surface as the outgoing rays. Okay, so this is the refracting surface. This is the outgoing ray from the surface, but this guy is on the other side. So image distance S prime is negative because the image is not on the same side as the object, obviously. Okay. Center of curvature. Well, the center of curvature of this thing is actually infinite, and it could be in this side or on that side, okay? Because this thing is not like that or either like that, which are the next steps that we're going to look at. But the center of curvature of a spherical reflecting or refracting, here we need that thing here that we don't have, curvature is positive, we need a slash here, if it is located at the same side as the outgoing rays. Okay, so let's say I have something with curvature like this. This would be a curvature that is positive. Something with a curvature like that would be a curvature that is negative. Okay, S is the object distance and S prime is the image distance. And in this particular case, S prime must be considered negative. This is part of the sign rules too. So we can look at the refracting situation now. See, this is the incoming, this is the surface. Okay, now we are inside the water. Let's say the surface of the water is the refracting surface. So the ray is incoming to the surface like that, and it's outgoing like this. The object distance in this case is positive because the object is on the same side as the incoming ray. Perfect. Image distance prime is negative because the image is not on the same side of the outgoing rays. See? So should be on the same side of the outgoing rays. The outgoing rays, S prime is negative in this case, and S prime is negative in this case because it's not on the same side of the outgoing rays. This is rather fictitious at this point, but it's good to learn because of what we're going to see later. Height of an image. How high is an image? Well, it's almost evident here. We take this point and we draw two rays. This ray that goes to the vertex here and comes out with theta, and this guy that goes normal to the surface. The one that goes to the vertex and comes out with theta means that this is theta, and this angle also is theta, okay? They are opposed by the vertex here, so this angle is equal to this one. And this guy is a straight line, so it's evident here that no matter what the position of the image is, we know that S prime is equal to S from what we did before. So this height here, Y prime, which is the size of the image, is equal to Y. So both images are the same. Essentially, in a flat mirror, when you look at it, and if the mirror is good, you'll see the size of everything the same size that you have on the other side. This is your familiar morning thing, see? You get into the mirror in the morning and look at the guy on the other side has the same size that you have. So the height of the image is the same. Yeah. The magnification is actually measure the relative size, Y prime divided by Y. This is the magnification, okay? Image from an image. Wow, this is great. The importance of finding images is that they can actually produce new images. Not in a flat system, but in a system with two flat mirrors, like it is here, okay? So I have one mirror here and one mirror here. I have the object here that produces an image there, and an object here, the same object that produces an image here. The distance from here to here is the same as the distance from here to here, okay? Now, you can see many things from here. For example, you can see, look at the rays that have been traced here, these two rays. They go into this mirror, they reflect back into this other mirror, and they get into your eye. So this image we knew from before, this image we knew from before, this image is a new image that is formed simply because it's an image of an image, okay? It's an image of this image in this point, and it's an image of this image due to this mirror. And they happen to be in the same position, okay? So you can, even though the mirror doesn't extend that way or that way, you can always say that this guy is going to produce an image in this surface. How can I? Simply because I can see it through this mirror, okay? If I can see it through this mirror, if I am in an angle through this mirror, I'm going to be able to see that image, okay? So what actually happens is depicted here, okay? So this light goes through here, bounce back from this mirror and bounce back from this mirror. And in those bouncing back, it produces an image in this place. You can also treat them just, you know, in a practical way and saying every surface should produce an image of every object. And an object could be an image. That's the interesting part, see? So this guy is actually reflected up here. The location of this guy is the same distance that this guy has to this mirror, because it's reflected in here and provides an image there, okay? Which is coincident with the one that if I extend this further that way, this guy will produce an image here. And how do I see that? Well, I have to see it from an angle that I have the options of actually seeing this object. So if you have two mirrors in perpendicular direction, you see three images of a single object, okay? That should familiarize yourself with that. You can do that also if you have two mirrors at home, okay? this experiment. Reflection from a spherical surface. Okay, so now the laws of reflections and refraction, keep being valid. This is a flat spherical surface where at this point, you have a normal that goes to the center of the sphere. The bright part is the inner part of the sphere. So this is a soccer ball. You cut in half, and you keep the shape, and then you just cover that with a reflecting surface, and you get this concave spherical surface. And B is the vertex. This is the axis, and then if I locate a point object here, light will go to the mirror. In this particular case, we get to this point, and at this point will ask me, what is the normal to this? Well, the normal it has to be measured with respect to the center of the sphere. Perfect. This is the center, and the angle that it will make will be theta coming in this direction. Okay, perfect. This is theta. This is theta. This is r. This is the radius of curvature of the sphere. And we have a bunch of angles and whatnot defined here. So why would this thing make an image? Because at least 2 points coming from this source just cross each other somewhere in space. See, this is a light ray that coming from this source, bounce back here and come back to some point in the axis. And this guy here is reflected normal from this point, because the normal here, so it's going to come this way and come back this way. So that's why we know that there is an image point at this particular point P prime. Okay. The rule of thumb is you can draw two lines that actually intersect after being originated from the same source point, and they will create an image. And that's point P prime, okay? In this particular case, following the rule of signs, S and S prime are both positive. This is S, the distance of the object. S prime is the distance of the image. And as you may imagine, what we want to do is actually find out how S and S prime relates to all the parameters in the system, okay? So I have the same drawing again. And I noticed that phi is the external angle of this triangle here. So phi is equal to alpha plus theta, which is the first thing here. Beta here is the external angle of this second triangle, the CP prime B triangle. And so beta will be equal to phi plus theta, which is the second equation. So I could rearrange, this is to get a sense of what we're doing and why I am doing it. The only angles that are really important are the angles made by the rays with respect to the vertical, to the optic axis of the system. So the angles that I have to find out how do they relate are alpha, phi, and beta. Why is that? Because that will give you something that relates to the distances. Something that relates to the distances is something what we are interested in getting. Where are the images formatting, okay? And using the geometry to do that. This is what we're doing here. So then I recognize that tangent alpha, the tangent of this thing, is equal to h divided by s minus alpha is s minus delta, not s plus delta. This is minus delta here. I'm sorry. I will fix it later, okay? And so, and the same here, beta is, tangent beta is h plus s prime, which is the distance from the vertex to the point of the image, minus delta. So this is sign is wrong and this sign is wrong. but this sign is absolutely correct. This, I don't know what came into my mind. Okay, so those two signs are incorrect, but simply by looking at this thing. So then I use this expression, and I assume all the angles are very small. So tangent alpha equals sine alpha. And if I do that, this is simply tangent alpha is equal to alpha, so it's h over s here. Delta, if the angles are small, this delta goes to 0, so it has almost no influence on nothing. So it's delta equal to 0, perfect. And then I have this relation. I get rid of the h's here. How do I do that? No. Beta, where's beta? Here's beta. It has an h missing here. Okay, if I want to get rid of the h, I have to put it first here. So this relation has an h missing at this point. Okay, these signs are minus, and there's an h missing here. So this is the final relation for the relation between the image and the object distance and the image distance with the parameters of the concave surface. 2 over r is called or r over 2 is called the focus, the f of this thing, because this is 1 over s plus 1 over s prime is equal to 1 over f. Okay, so this is simply the rules of the objects again. So what you will see is that if we have a concave region, r is greater than 0. If we have a convex region, the center of curvature is on this side. This is the outgoing rays. So the r value will be less than 0, and this relationship will hold true for both. Will hold true for this and this if we just follow the sign rules. Okay, for s and for r, for s prime and r, we follow the sign rules. Okay, and this expression for image formation is the same. You know, this is the interesting part. I don't have to do the deduction all over again. Okay. This is an interesting aspect. When parallel rays are incident on a spherical mirror, the reflection goes through the focal point. So see, this is the center of curvature here. From the center of curvature, I draw a line which is normal to this point. So the angle with respect to the normal, this angle theta will be equal to that angle theta here. If I do that construction for every point on the inner part of the sphere, what I get is that the reflecting rays, goes right through the same point, the focal point. So a set of parallel rays, what gives parallel rays? Parallel rays are given by something that is, very far away. Because very far away, there's no way there's going to be an angle with respect to this is a finite size, and very far away could be a kilometer or astronomical distances in case of telescopes or something like that. So this goes here, bounce back to the focus. How does it look here? It looks like the object is at infinity. If the object is at infinity, 1 over s, where s equal infinity is 1 over infinity, this is 0. And 1 over s prime is equal to 2 over r, and this is by definition 1 over f. The image is formed at the focal point, and the focal point is exactly half the radius of the sphere, of the inner sphere. Perfect, s prime is equal to r over 2, equal by definition to f, okay? Now, if I place the object that it's emitting light at the focal point, you know, the exact reverse happens. You know, if you take away this line this way and look at this, the thing goes to the spherical mirror and is bounced back in parallel form. Okay, so this is, you know, this is what was used to produce, you know, in the early age of cinema. You know, this is something you would like to have. The film, the old film that was a piece of cellulose tape going through this thing here in front, and here we had a filament, very intense filament, located in the focal point of a reflector that actually produced a parallel set of rays. Actually, it wasn't parallel really. It was a little bit. This guy was a little bit further in, so the rays would not go parallel, but will go somehow opening towards the screen. So the image on the screen will be a bit bigger. Okay, so because the size of the film is a few centimeters across, and the screen where you actually see the movie it's meters apart. So this was the trick to actually get a high intensity source illuminating uniformly the cellulose tape. Okay. So if the object is placed at the focus, it means that the object is 1 over f. This is the object, and this is 1 over s prime, and this is 1 over f. It means that s prime, the image, will form at infinite. Yeah, because the only way these guys will be traced back to somewhere, it will be that these guys are going to be parallel up to infinity. Okay, so this is sort of the checking point of the formula we have just deducted. Okay, 14, 15. Okay, so I have 2 minutes left according to my accounting, and I'm nowhere where I would like to be. Okay. What page? Oh, wow, 17 of 27. Okay. Okay, I knew this was long, but not that long. Okay, let me. This is the same subject. Now, what I want to do, this is the position. What we found out here, there's a way to find the position of this object, of the image of this thing in this plane. And if the object is a finite size object, and let's say it's an arrow that goes in that direction, what will happen here, we will also have an arrow in the same direction, will be formed in this direction. Okay, so what I would like now to do is take a finite size object and find out what is the magnification of the image in this particular situation. So this is the construction that I have. So I have an object here, and I have 2 particular rays that are intersecting at this point. If 2 rays, remember that, if 2 rays intersected, then there's plenty of more that they will do the same trick, okay? So one of them is going right through the middle of the mirror here, bounce here, and this angle will be equal to this angle over here, okay? So this triangle actually happens to be similar to this triangle here, meaning there's a proportion between this side, that side. We have to find what are the similarity angles here. So the similarity between the components, and this angle is equal to that one. This is a simple construction because it's reflecting from this here, this point here. The normal is normal to the optics axis. the reflecting surface is normal to the optic axis. The second one is a nice trick, because something that goes directly through the center of the reflecting surface will arrive normal to the surface. And if arrive normal to the surface, it will bounce back in the same direction. Now we have two axes, two rays that intersect each other at this point, and the position of the intersection will be the corresponding image of this object. So this object is actually made an image at this point Q here, Q prime actually, okay? The image are Y prime, Q prime, and the object is YQ, okay? So we define the magnification of the systems as the ratio of Y prime, this guy, versus Y. In this case, the magnification is less than 1. It means that this image is actually smaller. And it actually has a sign, because actually it's inverted. So this is the reason why the magnification has this thing here. Actually, if I look at the distance, I find out that this distance over here is to this distance over here. I'm sorry. PQ is to P prime Q prime as VP is equal to VP prime. Okay, so the ratio of the two things, because these are similar triangles, should be the same, and I can use that to actually derive the magnification of this sample. So what do we know now? We know from this equation, no, that's not the equation, that's not the equation. From this equation, remember these signs are negative, and I'm missing an H here, okay? But this equation is correct, okay? This equation here is correct. From this equation, we know what the position of the image is. And from this equation, we know the size of the image, okay? You have to introduce the correct sign for S prime and S in this relationship too. Okay, I'm very sorry I'm not done with this, but I think I'm going to continue next session. It was not in the planning, but that's going to be it. Okay, so this is it for today. I hope it wasn't that boring. This is very simple, but there's a lot of geometry in this thing, as you can see in this image here. And as you can see, we are treating electromagnetic waves as rays, no diffraction whatsoever. Okay, the image produces perfect shadows and whatnot. This is what is called geometrical optics, and it's very good for many practical reasons. And the image formation in a complicated optical system, this is the first thing that you have to do to actually understand from the point of view of technical engineering how you work out the solution of devices. Okay, so I'm working on this just so you can understand how a telescope works, how a microscope works, how your eye works. I'm not gonna do that myself. You guys have to study that, because otherwise it's going to be too long. But I just wanted to share with you the idea of what are the basic elements that you need for order to understand how an actual optical instrument works. Okay, so what we are seeing here, these are the optical elements. Okay, we're going to finish next class with this. Okay, so my apologies, because I was trying to cramp in so much subject on the matter. So let me